we can use our knowledge of pKa values to actually calculate equilibrium constants for an acid-base reaction. So, for example, if we were to take sodium anide, NaNH2, and the Na is a spectator ion, so it's not really going to be important. And we were to react that NH2 minus ion with hydrogen cyanide, we would expect an acid-base reaction. The aniline is a pretty strong base. Hydrogen cyanide is an acid. We would expect that to be in equilibrium with ammonia, NH3, and cyanide ion. Ammonia would then be our conjugate acid, and cyanide ion would be our conjugate base. And we might want to ask ourselves the question, where does this equilibrium lie and how strongly? Is this reaction going to go to completion? Is it going to go hardly at all? Or are we going to have significant concentrations of both HCN and cyanide ion when we're done? And this reaction could happen in liquid ammonia, or it could happen in liquid HCN. Both of those can be liquefied relatively readily, or it could happen in soluble organic solvent. So what we'd like to do is calculate the equilibrium constant for this reaction. And we can do that if we know the pKa value for HCN, which we do. It's around 9 to 10. And the pKa value for ammonia, which we know is about 35. So we know both the pKa for our acid and the pKa for our conjugate acid. It's somewhat arbitrary which one I call acid base and which one I call conjugate acid, conjugate base. Conventionally, the things on the left are labeled acid and base, and the things on the right are labeled conjugate acid and conjugate base. Usually the reaction is written, in general chemistry anyway, so that the weaker acid-base pair is on the right. So the conjugate acid is weaker than the acid, and the conjugate base is weaker than the base. I've written it that way, right? 35 is a much larger pKa value, and therefore a much smaller Ka value than 9. So we know that this is a much stronger acid than that. So we in fact know that this equilibrium is going to lie relatively strongly to the right. But how strongly? What's the actual numerical value for the equilibrium constant? There are two ways to approach that. Certainly we can write the equilibrium constant for this reaction, because the equilibrium constant is always defined as the concentration of the products divided by the concentration of the reactants. But I don't actually know any of those concentrations, so I can't simply plug those concentrations in. But what I do know is I know the equilibrium constant for this reaction. HCN associated to form H plus is Cn minus. That's a Ka expression. And I know that Ka, which is equal to 1.0 times 10 to the minus 9, is equal to the hydrogen ion concentration times the cyanide ion concentration divided by the concentration of the HCN. And I also know the equilibrium constant for this reaction. And it is 3 associated to form H plus and H2 minus. Because again, that's a Ka. And I know that for this reaction, Ka is equal to 1 times 10 to the minus 35. That's equal to H plus concentration times H2 minus concentration over H3 concentration. So what I need to do is I need to do something to that equilibrium constant expression here to allow me to pull out these pieces and then assign their numerical values. So I can pull an algebra trick I can multiply by hydronium ion concentration, or hydrogen ion concentration, divided by hydrogen concentration. It's always okay to multiply something by 1, right? X over X, in this case, hydrogen ion concentration divided by hydrogen concentration. That's simply multiplying by 1. And then I can group my terms so that I have hydrogen containing pieces and the hydrogen ion denominator associated with the ammonia containing pieces. It's now fairly clear that this is the Ka expression. And so I can substitute in for that bit 1.0 times 10 to the minus 9. Is the reciprocal of the Ka expression. So this is actually for the equilibrium reaction H plus NH2 minus going to NH3, right? Concentration NH3 in the numerator, concentration of hydrogen ion in NH2 in the denominator. But since that's the reaction written backwards, the equilibrium constant for this reaction is equal to 1 over Ka. And this piece is equal to the reciprocal of the Ka expression. So for that piece, I can plug in 1 over 1.0 times minus 35. And 1 over 1 times 10 to the minus 35 is 1 times 10 to the 35th. So my equilibrium constant is now equal to 1.0 times 10 to the minus 9 times 1.0 times 10 to the 35th. So it's therefore equal to 1.0 times 10 to the 35 minus 9, which is equal to 1 times 10 to the 26th. That's a very large equilibrium constant. So completion. And H2 minus is a very strong base, and it's going to succeed in completely deprotonating the cyanide ion to form ammonia, or the HCN rather, to form ammonia and cyanide ion. Multiply by H plus over H plus and then group our terms. The other way to accomplish the same thing is to try to write the overall reaction that you're looking at as the sum of two other reactions for which we know the equilibrium constant. And then if we add reactions, we know we multiply equilibrium constants. So if we can write that reaction as the sum of two other acid-base reactions, we'll be in business. So let's talk about phenol. Which we know has a pKa on the order of around 10. Let's talk about phenol reacting with NaN3. Again, the Na is a spectator ion, so we really need to know about the N3 minus ion. N3 minus ion looks like this. Azide ion. And one of the reasons why HN3 is a stronger acid than NH3, for example, right? HN3 is about 5. Is because that's an sp2 hybrid, which means that the nitrogen that's containing the anion in the azide ion has greater S character than for ammonia, significantly stronger acid. So we know the sodium is a spectator, we're going to leave it out. We're going to write this reaction as phenol reacting with N3 minus, or the oxide ion, and HN3. And we'd like to know the equilibrium constant for that reaction. So how can I go about doing that? Well, what I can say is, let me just think about phenol losing the hydrogen. Form for an oxide ion, and H plus. I know that equilibrium constant, that's Ka. Ka is 1.0 times 10 minus 10. And then in a separate reaction, when we talk about hydrogen ion reacting with N3 minus, form an HN3. That's not a base dissociation constant, right? That's not Kb, because there's no water involved and no hydroxide. That's the reverse of the Ka expression. This is Ka written backwards. And H3 associated with H plus, sorry, HN3 associating H plus and N3 minus. That's the Ka expression. That's the backwards Ka expression, which means that the equilibrium constant for this, 1 over Ka, which is equal to 1 over 1 times 10 to the minus 5. If I add those two reactions together, hydrogen ion cancels out, and I get the overall reaction that I was looking for in the first place. Phenol reacting with azide ion to form an oxide ion and HN3. I can simply multiply the equilibrium constants. In this case, KEQ is equal to Ka. In this case, KEQ is equal to 1 over Ka. So the equilibrium constant for this reaction is equal to Ka1 and 1 over Ka2. If you consider this one to be the second reaction and this one to be the first reaction, and that equilibrium constant is therefore equal to 1.0 times 10 to the minus 10 times 1.0 times 10 to the fifth, which is the reciprocal of the Ka expression for HN3, and that's 1 times 10 to the minus 5. So the equilibrium constant for this reaction is equal to 1.0 times 10 to the minus 5, and that reaction lies almost exclusively to the left. The azide ion is a weaker base than the phenoxide ion, and therefore is not a good enough base to deprotonate the phenol. You should be comfortable with doing this calculation in both of these ways by algebra manipulation, multiplied by H plus over H plus, and more intuitively, I think, by dividing it up into an acid reaction written forward and an acid reaction written backwards. I would expect you to be able to derive the expression that tells us how to use the two Ka values. But if you're not really comfortable with the derivation, you can always just memorize how to do it. So if I were to take amide ion, NH2 minus, well, let's use amide ion, let's not use amide ion again. Acetylide ion. So if I were to take sodium acetylide, for example, NaHC2, and I were to react that acetylide ion with acetone, and I want to know if that's a strong enough acid to deprotonate the acetone to form CH2CO CH3, which we know is resin stabilized, and acetylene. The equilibrium constant for this is equal to the Ka for the base on the left, and conjugate acid, conjugate base on the right. So if I know the Ka value for the acid, which I do, it's about minus 1 times 10 to the 20, or 1 times 10 to the minus 22, and I know the Ka for the conjugate acid, its pKa is 25, so its Ka is about 1 times 10 to the 25th, or minus 25th. Right. So for the aldehyde, about 20, and therefore Ka is 10 to the minus 20. For the ketone, it's more closer to 22. I can simply plug those values in. 1.0 times 10 to the minus 22, 1.0 times 10 to the minus 25, and that's equal to 10 to the third. Anytime we have an equilibrium constant that's bigger than 10 to the third, we say the reaction goes to completion, and we effectively have a one-way reaction that's no longer in equilibrium. This is right on the borderline. This is on the order of 10 to the third. So it's a strongly favorable reaction. The weaker of the two acids is the acetylene versus the acetone, and so it lies towards the weaker acid. You can even get this from pKa values directly by recognizing that your equilibrium constant is equal to 1 times 10 to the pKa of the conjugate acid minus the pKa for the acid. So in this case, the conjugate acid has a pKa of 25, and the acid has a pKa of 22, and so that's 1 times 10 to the third. You can memorize that. KQ is equal to 1 times 10 to the pKa of the conjugate acid minus pKa of the acid. But of course, on a quiz or an exam, I'm going to expect you to show all the work that shows how you get there. And the fastest way to get there would be to recognize that this can be written as the sum of the acetylide ion picking up a hydrogen, glutathione acetylene, added to acetone losing a hydrogen. The base. Some of those two reactions cancel out the hydrogen ion and gives us the overall reaction. This is the Ka expression. This is the inverse of the Ka expression. So that gets us the same equation where we're looking at the Ka of the acid divided by the Ka of the conjugate acid to get our overall equilibrium